Nathaniel.
Yeah, my name is Nathaniel Roble, and this summer I worked on training a quantum convolutional neural network to correctly detect the phase of one-dimensional transistor Ising chains. The transistor Ising model is a popular many-body system that we use to identify phase transitions. And we can define this model as a lattice structure. So we can have a lattice structure of an n number of sites, however many we need. And here we have a representation of a two-dimensional lattice with 9 sites. And each site can be in one of two states, +1 or -1 in our case. And right below, we have a Hamiltonian equation. We can use this to calculate the total energy in the system, depending on the orientation of the spins in these specific sites. And we use J to represent a coupling constant. And because these sites in the system can interact with their neighbors through coupling, so we can represent that with J in the equation, and you can see we're summing the total interactions of all our neighboring sites. And the second term in our equation introduces an external magnetic field. And this external magnetic field is going to interact with each site individually. So we're summing those individual reactions as well. We also have our phase diagram, which we can use to plot the phase transitions, where we have temperature on the y-axis and an order parameter on the x-axis. So we're working in a computing environment. So we have 0 temperature. And at 0 temperature, you can see this convergence where we have a quantum critical point. And this is going to signify the phase transition from one phase to the other, with left being an ordered phase at a paramagnetic system and right being a disordered phase with a paramagnetic system. And we use this model in quantum computing. And quantum computing allows us to use quantum mechanical properties to perform computation. Some of these properties include superposition and entanglement. So superposition allows us to put a qubit, the classical analog, or the quantum analog of the classical bit. We're able to put it into a superposition of both the 0 and the 1 state. So it can't be defined as one or the other, but both. And then entanglement allows us to take multiple qubits and entangle them, meaning if we measure the state or change the state of one qubit, it could directly affect the state of a different qubit when they're entangled. So we can't describe these qubits independently of each other. And in quantum computing, we're able to construct quantum circuits. So we can have any number of qubits for our input. Here on the left, we have 2 qubits for our input. And then we enact a series of quantum gates in any order we want. We have 2 here. We have a Hadamard gate acted on the first qubit, so Q0, and then a C0 gate, which is able to entangle these 2 qubits. And when we construct our quantum circuit, we can change the state of the input qubits to get the desired output. And in quantum computing, we can construct quantum algorithms to solve specific problems. And the algorithm that was used in our data sets is the variational quantum eigensolver. So this algorithm uses the variational method to find close approximations to the ground state of the system. When we don't know the system's true wave function, so we can't calculate its true ground state, we can define a trial wave function. It can be arbitrary or it can be an educated guess. But when we define this trial wave function, we make it depend on some set of parameters. And as we change the value of these parameters, we can notice the calculated ground state for this trial system to go up and down. And when we find that minimum value for the ground state, we know what set of parameters we need, and we have a good approximation to the true ground state of the true wave function. So in quantum computing, we can construct our trial wave function by constructing a circuit. Here we have a 4-qubit circuit with a series of gates acted on them. And we made these gates depend on some parameter values. And when you sweep a range of these parameter values, you can find which set of parameters give you that ground state that you're looking for, so you have your good approximation. And each qubit in this circuit is going to represent a site on the transistor Ising model. So here we have a one-dimensional system with 4 qubits or 4 sites. And through the variational principle, we know that the approximated ground state that we calculate with our trial function must be greater than or equal to the true ground state of the true system. And using this algorithm, we were able to import a data set. So we didn't do this ourselves on this data set. We just imported it for the purpose of training our neural network, but a little background on the data set that was handed to us. We imported it through TensorFlow. So they were given this Hamiltonian, and G is going to be the order parameter. And this order parameter can range from 0.2 to 1.8 in this scenario. So what they did without knowing the true wave function, they constructed their trial circuit with 4 qubits as well, made their gates depend on some value of the parameter, and then they used a value for G. So we'll start with the first data point using the value of 0.2 for G in that Hamiltonian. So for that value of G, they wanted to calculate, or they wanted to find the set of parameters that give that minimum value for the energy. And then they went to the next value of G. And then using 81 different values of G in this range of 0.2 to 1.8, we were given 81 data points, each representing a trial wave function. And all of these wave functions or circuits are constructed exactly the same as you see here. The only difference is the value for the parameters because of the varying value of G. And G represents or gives us the phase of the system or the label. So any value of G that was less than 1, we have a ferromagnetic system. Any value of G greater than 1, we have a paramagnetic system. And our G equals 1 gives us our quantum critical point where we see a phase transition happening. And another thing on this data set is we noticed that the variational parameters were continuous. So we were able to interpolate the data to create as many data points as we needed, which was very useful in training our neural network. And the quantum convolutional neural network is useful for detecting and classifying quantum data. So what we wanted to do with this neural network was to try to get it or train it to correctly label each wave function or circuit with their corresponding phase. And what we needed to do was we needed to construct a neural network that had a series of convolutional and pooling layers. So the convolutional layer is represented at the bottom. Its main purpose is to find key information or hidden data within pairs of qubits and send it along by enacting X, Y, and Z rotations on that qubit. The pooling layer tries to take information from pairs of qubits and pull it down to just one qubit and reduce the degrees of freedom. So we can systematically shrink the size of our system down from 8 to 4 to 2 to 1 qubits every time we enact a pooling layer. And once we get down to our final qubit, we can make a measurement on that qubit and find out if the predicted value for the label was correct or incorrect. And regardless if it's wrong or right, we have a value for the loss through the mean squared error, which kind of tells us how far off the prediction was from the true value. And during the training phase, the QCNN uses back propagation to change a set of parameters that are enacted on these specific layers that are on the gates in the layers. And then once it finds a good set of parameters that can make the loss converge, we know that our QCNN is fully trained. And the QCNN is also constructed in a circuit environment. So what we can do is we can just put the wave function circuits on the front end of the series of convolutional and pooling layers. So at the end, we just have one really long circuit that does everything we need. As we input our trial wave function, we go through the layers to take out the important data and pull it down, and then we get our measurement. And I did these tests with system sizes of 4, 8, and 12 qubits or sites, all one-dimensional. And you can see here we have pretty good results for the accuracy in that 99% range. So even as we increase the number of qubits for our input, we still were able to conclude that the QCNN was capable of predicting the phase of the wave functions. And then for our loss, same system sizes, we can see here that the loss is converging as we train the network. And we can see that as we increase the size of the system that we input in our wave function, our loss goes up. And this is expected because we have more input variables, so we're going to have more room for that loss to grow. But at the end of the day, you saw that our accuracy was still high. We still got that 99% range for our system sizes of 12. So regardless of this increase in loss, we know that our system or our network was capable of predicting the phase of systems for each size. This is a summary of the results that I just discussed. And from this, we concluded that the QCNN model is a feasible method to classify quantum data using this model. And from here, we would like to push the limits of a quantum convolutional neural network by implementing more complex systems. And some ideas would be to use the same model with more complex Hamiltonian equations. We could test our neural network using different many-body systems, or we can construct our own neural network model for testing and generate our own data sets using the variational quantum eigensolver. Questions?
Well, Natalie, I would like to know, I mean, you didn't know about all this at the beginning of the program. So what has been your thought going through these last 10 weeks?
My thoughts through the program is I definitely enjoyed it. I didn't know anything about quantum mechanics, coding, machine learning, so I definitely learned a lot, and it was difficult at first. But I can say overall, I really enjoyed the program and the research that I was involved with, as well as the mentor, Dr. Coming or Professor Coming, that helped me through this research. So I'd like to say thank you to him as well.
Jonathan?